Hello and welcome to this clip on phenols. We'll start by having a look at some of the differences in reactivity between benzene and alkenes, so then we can use that as a context or a backdrop against which we can look at the reactivity of phenol. We'll then use the structure of phenol to try and explain this slight difference in reactivity, and then we'll have a quick review of some of the typical reactions of phenols that enable us to distinguish them from other aromatic compounds. So this clip will assume that you've already have some confidence and familiarity with the basic electrophilic substitution mechanism, and you've applied it to nitration, halogenation and alkylation and acylation of the benzene ring. So phenols should really be looked at after you've made yourself comfortable with those different reactions. So if you're in any doubt, it might be worth going back and looking at your notes and your textbook on those areas before proceeding any further. So first let's do our review of reactivity in benzene and alkenes. So as you're probably already aware, benzene has a delocalized system of p electrons. We sometimes call this a pi system because it's made of pi bonds. So the pi bonds in this, for example, would be these regions above and below each carbon atom. So because they overlap sideways above and below the ring, they lead to the structure that you can see on the right hand side of the screen. So basically this stabilizes the ring, and as you know makes it resistant to electrophilic addition, because the electron density which electrophiles would otherwise be attracted to are not localized in one area of the molecule. So for this reason benzene reacts via electrophilic substitution. Now this is the scope of explaining electrophilic substitution is best left to the other clips that we've done on that particular area. There's plenty of clips on it on YouTube anyway, but this is just really to remind you that benzene doesn't undergo electrophilic addition at all because there's not enough localized electron density anywhere in the molecule for electrophiles to be attracted to it. So if we were to quickly look at cyclohexane, for example, it will behave exactly the same way as a normal alkene such as ethene or propene. So as you can see, the pi bond is only in one place. It's localized. So because it's only in one place and it's not in a delocalized format, basically any incoming electrophiles are first of all attracted to it, and secondly they can also be polarized by it because it's an area of electron density that is in one place. So this idea of the area of electron density being in one place is called localization. In benzene it's called delocalization because the areas of electron density are not specifically bound to one position in the molecule. So for this reason cyclohexane reacts really easily with electrophiles by electrophilic addition. So this is sort of a review of some of the things that you looked at when you first did alkenes in your first year. So now let's have a look at phenol and see how it fits in amongst those two different ways of reacting. One is electrophilic substitution, the other one is electrophilic addition in the two different compounds. So looking at phenol, it's basically a benzene ring that has an OH group attached to it. So I'm going to add the hydrogens to the benzene ring section of the phenol molecule that I'm drawing at the bottom. And in exactly the same way as you draw the delocalized pi system for a benzene ring, you can similarly do a delocalized pi system for a phenol. So I've drawn in the p orbitals that are above and below each carbon, but oxygen also has p orbitals. And you'll also probably worked out that oxygen is likely to have lone pairs. So this brings an interesting angle to the electron density part of the benzene ring in phenol. So although you've got the p orbitals as you would have in benzene, you've also got the sideways overlap of the p orbitals as you'd have in benzene. The fact that you've now got an OH group attached directly to the benzene ring via the oxygen atom means that the lone pair on the oxygen, or one of them, is incorporated into the pi system. Now if you remember, the pi system in normal benzene has 6 electrons, 1 electron from each carbon. If you now add 2 electrons to that, the lone pair from the oxygen, you have a total number of 8 electrons in phenol's pi system, So now we've got some extra electron density. That now means phenol can attract and induce dipoles and electrophiles much more easily than benzene can. So it can do a lot more reactions than benzene can. So phenols are essentially more reactive than benzene for this reason. So if you're looking at a structure and you're trying to work out whether it's a phenol or not, all you have to do is see if there's an OH group attached to the benzene ring directly. So the first two have an OH group attached directly to the benzene ring, like so, but the third one doesn't. So the third one is not a phenol, but the first two definitely are phenols. So salbutamol is an example of a drug, a pharmaceutical, that's a phenol. So what it does is it causes the airways, the little bronchioles in your respiratory system, to dilate, allowing a greater flow of air into the lungs. If you suffer from asthma, what happens during an attack is the airways start to constrict. And as they constrict, that means less air can move through them into your lungs, so you find it difficult to breathe. What salbutamol does is it attaches to receptors on the surface of the muscles that are on the outside of the walls of the airways, and they cause the muscles to relax. That means the airways get bigger, more air comes in, so you inhale, use the inhaler, and then your breathing can slowly start to resume to normal levels. So in terms of phenols, you can see quite clearly there's a benzene ring. Yes, it's drawn in the Kekule fashion in this particular diagram, but that part of the molecule there is the phenol. So salbutamol will do all the reactions that we're about to start looking at to try and illustrate the chemistry of phenols. So basically what happens is a phenol can behave first of all as a weak acid. For it to do so, you have to be able to release a proton. So if a proton can be released, then your substance can be described as an acid. In order for that to happen easily, the rest of the molecule that's left behind has to be stable. So let's put a little bit of flesh onto that. The phenoxide ion that is left behind needs to be stable enough to exist on its own for a short amount of time, or at least in solution. So the delocalization of the lone pair on the oxygen atom within phenol's OH group means that the OH bond breaks easily. However, at the same time, I'm sure you've noticed that there's a reversible sign. This means that although this process can happen, for every mole of phenol that you've got, not all of it will actually end up dissociating into phenoxide and H+. So there we consider phenol to be a weak acid as opposed to a strong acid. There's a way you can illustrate this. So you can easily get phenols to react with strong bases such as NaOH. So other weak acids like carboxylic acids such as, propanoic acid, ethanoic acid, etc., they'll also react with strong bases such as NaOH. So if you were to do the same comparative reaction with a weak base such as sodium carbonate or sodium hydrogen carbonate, the phenol won't react, but the carboxylic acid will. So this is an interesting way of telling the difference between a carboxylic acid and phenol in terms of their acidic behaviour. So if you look up at the top of the screen, you can see quite clearly that if you have a carboxylic acid reacting with a weak base such as sodium carbonate, you'll get a sodium carboxylate salt, hence the Na plus RCOO minus, and you'll also get CO2. So the CO2 will actually show as fizzing. So the fact you can see effervescence and fizzing when a carboxylic acid reacts with sodium carbonate, but you won't see anything when phenol reacts with sodium carbonate, makes this a good diagnostic test in a laboratory to tell the difference between phenol as a weak acid and a carboxylic acid as a weak acid. So this might definitely be one to consider putting on a flashcard for future reference. So sometimes what you might get asked about is why phenols can behave as weak acids but alcohols cannot. So if we take phenol and compare it to methanol, for both of those compounds to behave as weak acids, what has to happen is that the proton has to be lost. So in order for the H plus to be released, the OH bond must break. So for that to work, the negative ion that's left behind when the H plus goes would have to be stable enough to exist on its own. If that's not likely to be the case, then the hydrogen is not likely to be released because the bond is not likely to break in the first place. So let's break the bond in both of these and see what we get. So you get your H plus coming off and you'll be left with a phenoxide ion in the case of phenol and a methoxide ion in the case of methanol. So going back to the structure of the delocalization within phenol, you remember that we talked about the delocalization of the pi system that also incorporates one of the lone pairs. That makes the phenoxide ion more stable because the lone pair is incorporated into the pi system of the benzene ring. So the phenoxide ion is more stable because the lone pair on oxygen is delocalized into the aromatic ring. But the methoxide ion is less stable because there's no delocalization, so it's less likely to form, and therefore the H plus is less likely to be released. So therefore the bond between the oxygen and the hydrogen within methanol is less likely to break than the bond between oxygen and hydrogen within phenol. So in a similar way, because metals react with acids, you'd expect metals to react with phenols because we've just talked about phenol's weak acid behaviour. And if you were to put some sodium, for example, into phenol, you'd be able to see fizzing, and the fizzing this time would be hydrogen given off. So like any other acid, you'd get a salt and hydrogen produced, and the salt created in this case would be called a phenoxide. So in this particular example, it would be called sodium phenoxide. An important thing to maybe look at is the mole ratio. So the mole ratio, 2 to 2, that's because H2 gas requires 2 protons to be given off, and only 1 proton is given off per phenol. So if you've got 1 proton released from each phenol molecule, then if you want a mole of hydrogen gas, you need 2 moles of phenol and 2 moles of sodium to make 2 moles of sodium phenoxide and 1 mole of hydrogen. It's always worth remembering your mole ratios, even though it's quite simple stuff by this stage, I'd imagine. It comes into everything that we do in chemistry, even the more complicated reactions. So never forget checking your mole ratios. So in a similar way, you'd expect sodium hydroxide to react with phenol to create sodium phenoxide, except this time it's water that's created as a side product, not hydrogen. Now we talked about phenols reacting with strong bases easily a few minutes ago. This would just be an example of one. So obviously if it was another strong base such as, I don't know, potassium hydroxide, it would be potassium phenoxide that you'd make. So it shouldn't be too difficult to see how that works. So if, for example, you were to take your sodium phenoxide and react it with, hydrochloric acid, for example, what would happen is because the phenoxide ion is relatively stable, like we've talked about, then therefore the sodium will dissociate away from it quite easily and recombine with the Cl- in the acid. So you've got 2 possible examples of that at the bottom of the page, including one that shows a need to have a look at the mole ratio. So for example, with H2SO4, because you've got 2 protons in H2SO4, then each proton will react with 1 phenol, so therefore you get 2 moles of phenol, so there's a 2 to 1 mole ratio between the sodium phenoxide and the H2SO4. So what I'm trying to say here, 2 moles of that, 1 mole of that, 2 moles of the phenol produced, 1 mole of sodium hydroxide. So it's always worth, as I've said before, keeping an eye on the old mole ratios, because they will throw one in just to see if you're awake. So looking at halogenation of phenols is a slightly different situation compared to halogenation of benzene. So to aromatic benzene, you usually need a halogen carrier to make the strong enough electrophile, which is your positively charged halogen ion, to disrupt the pyrene and then initiate the electrophilic substitution mechanism. So if you remember that phenol actually has 2 extra electrons in its pi system because of the delocalization of the lone pair on oxygen into that pi system, that means phenol has 8 electrons within the pi system as opposed to 6 electrons within benzene's pi system. So for this reason, electrophiles in general are more easily attracted to phenol and dipoles are more easily induced in them. So this means that the reaction that's printed on the screen can actually be carried out at room temperature with no extra help or assistance from a halogen carrier. So therefore we need to be able to write down what the observations might be if we were to carry out this reaction. So first the bromine is decolorized and also a white precipitate of 2,4,6-tribromophenol is formed. So we'll also be required to write the equation. Now the equation is, you've got to be careful here because you need to think how many bromine atoms you actually need. If you think in total, the number of bromine atoms that are on the phenol, the substituted phenol, are 1, 2, 3. But bromine comes as Br2. And you also need to take account of the fact that the hydrogens that came off the phenol have been substituted, so there's a further 3 bromines that end up as HBr. So 6 bromines in total are needed, hence why we use 3Br2 on the left hand side. So if you were to write this equation out as a structural equation, as opposed to one that has the skeletal formula of the benzene ring in it, you can also do that if you wish. So I put it down there in purple, and I've also put a little note to avoid molecular formulae as they give no indication of functional groups. So try to stick to structural formulae as a bare minimum. Otherwise what's going to happen is the examiner is going to think, well, this person has given me a molecular formula, but how do I know they're writing about a phenol? So you need to be a little bit careful of falling into that trap. Quite a few people end up doing that without thinking. So take a moment to pause and decide what type of formulae you want to use before you write down your answer in an exam question. So phenols have a long history of being used as antiseptics, but pure phenol itself is actually quite corrosive anyway to human tissue, so it also does quite a lot of damage. As well as killing germs and bacteria, it destroys healthy cells as well. So nowadays we use substituted versions like 2,4,6-trichlorophenol, or TCP, that you can buy in the shops, or Dettol, for example, is 4-chloro-3,5-dimethylphenol. So the antiseptic properties of the phenol functional group is still actually in use, but what we do is we substitute other things onto it to try and reduce its corrosive nature onto human tissue. So now let's have a look at an exam question of the type that you might find in your paper. So looking at the first part, it says compounds 1 to 4 are all aromatic hydroxy compounds. So what do we mean by an aromatic hydroxy compound? It basically means a benzene ring with an OH group involved somewhere. So when I say somewhere, it can either be directly attached to the benzene ring and be a phenol like we've talked about before, or it could be directly attached to a substituent of the benzene ring and be an alcohol, an aromatic alcohol. So the phenols in this one are going to be all the ones that have the benzene ring with an OH group attached next to it. So we've got this one's a phenol, this one's a phenol, and this one is a phenol. The one that isn't a phenol is that one, because if you look closely, you'll see that the OH group isn't directly attached to the benzene ring, it's attached to a C that's attached to a benzene ring. So the OH group there is not attached directly to the benzene ring. So like we've said throughout this clip, to be a phenol, a substance must have a benzene ring with at least one OH group attached directly to that benzene ring. So in the second question, to demonstrate its acidic character, phenol can be dissolved in aqueous sodium hydroxide to give a colourless solution, A. On adding dilute hydrochloric acid, this solution becomes cloudy at first and then separates to give a colourless oil B as a lower layer. Identify A and B and write equations for the reactions involved. So what I'm going to do at this point is I'm going to move the screen up a little bit, the question up the screen, so we have a bit more room to have a look at it at the bottom. So the first one should be fairly easy to work out. We've talked about sodium phenoxide earlier on in this clip that you get when you react sodium hydroxide with phenol. The second one requires a little bit of deduction as to what's going on. So like we looked at before in this clip, we did sort of consider what would happen if you took sodium phenoxide, for example, and added an acid to it. You'd regenerate the phenol and give a sodium salt. So here you're adding dilute hydrochloric acid, so therefore it shouldn't be too difficult to work out that you get a phenol, or you get phenol back as the identity of B. So those would be your two equations, and obviously you could do the structural versions as well. So although it's maybe a little bit squeezed, you can hopefully make out that you've got the displayed, or the equation using the skeletal formula of your aromatic compound, but you've also got the equation at your disposal if you wish, using the structural formula of the aromatic compound. So I've just changed them to a slightly different colour so you can see what I'm talking about. So the next question asks us to give two reasons which together explain the fact that phenols are acidic, although alcohols have almost no acidic properties. And we looked at this in some detail earlier on in this clip, so it shouldn't be too difficult to cast your mind back and have a think about what to put here. So the first reason is the lone pair of electrons in the oxygen is delocalized into the aromatic pi ring. That allows the OH bond to break easily, releasing H+ in phenols. So therefore the phenoxide ion is stabilized due to that delocalization we've talked about before, but this can happen in the alcohols because the OH group isn't directly attached to a benzene ring, so the delocalization of the lone pair from the oxygen into the benzene ring can't happen. So notice in the next question what it says is to state what is observed. Now we spent a bit of time having a think about that, didn't we? So I would be careful here to make sure you're writing down what's actually seen, not necessarily the names of the compounds that you think are being made. So what you're after here is either white precipitate or decolorization of bromine water. So it says write an equation for the reaction. I'm going to try and fit in the skeletal formula for the compounds, the aromatic compounds, but I'm also going to put in blue, like I did before earlier on the page, the structural formula for what's going on. So we've got an attempt, I'm afraid, to squeeze in the skeletal formulas for the phenol and the substituted phenol, and in blue you've got the structural version if you wish. So let's bring the page down to have another look at the last part. So the next part of the question, for 3 marks, asks you to account for the relative ease of bromination of phenol compared to benzene. We talked about this at the beginning of the clip. So the lone pair of electrons on oxygen are delocalized into the aromatic ring's pi system. I should really say that oxygen is within the OH group in phenols. So that lone pair is delocalized into the aromatic ring's pi system, which then increases the electron density in the ring compared to benzene. So electrophiles are more strongly attracted to the benzene ring within phenols, whereas a dipole can also be induced more easily. And like we've just talked about, one use of phenols in everyday life as antiseptics or disinfectants. Okay, so now let's have a box scheme. So just going back over what we did, we've got 1, 2 and 4, it's all good. The basis of the identification is a phenol must have at least one OH group, we've got that. We worked out it was sodium phenoxide. I would avoid using sodium phenate, so as I go through this I'm just going to highlight anything that I think might cause confusion, so get rid of that. And it's mainly phenol is the identity of B. So the equations, we all got them, so all of that lot was fine. we could also say that if we wanted. So the lone pair of electrons on oxygen, point 1, is drawn into the benzene ring, or delocalized. I would say delocalized. Probably slightly better instead of drawn into or drawn towards. So delocalized into the benzene ring. The OH bond is weakened or polarized, so the H plus is lost relatively easily. You could say it's broken if you wanted to. So the H plus being lost relatively easily will also give you the fact that it's an acid, or acting as an acid. So the phenoxide ion is stabilized at the bottom by delocalization of the negative charge. You could say the delocalization of the lone pair on oxygen. So this encourages the dissociation and the formation of C6H5O-, releasing H+. This can't happen in an alcohol, so it's not possible for alcohols to act as acids in the same way. So in the next one, there's a white precipitate. You could also say, if you wanted, that Br2 is decolorized. The equation as such, you could also use structural as well. And then finally, the lone pair of electrons on the oxygen, they keep coming back to this, is drawn towards, so like we said, delocalized. So therefore, electron density on the benzene ring is increased, and the electrons of electrophiles are more strongly attracted. You can also say dipole induced. More easily. And then finally, antiseptics or disinfectants will get you the final mark. Okay, so thanks for your time on this clip. Hopefully it has helped you understand phenols a little bit more and how you'd apply the information to a typical exam style question. If you have any further queries, don't hesitate to contact your teacher, or maybe pop into one of the subject extensions to clarify in your mind what's going on. So in the meantime, thanks for your time and appreciate